Hey, my name is Lakshay, and this is my assignment 4 presentation. In this notebook, I'm going to demonstrate overfitting in CNN convolutional neural network using the CIFAR10 dataset, and then show multiple techniques on how I reduced it using L2 regularization, dropout, data augmentation, and controlling over parameterization. So in the first section, I'm using TensorFlow and Keras in the dataset for the CIFAR10, which possesses 60,000 color images at a 32 by 32 pixel and across 10 classes like airplane, cat, dog, truck, and so on. So for the data preparation part, I normalized the pixel values from the original 255 range down to a binary range of 1, 0 by dividing them from 255, and this helps the model train more efficiently. And then when we scroll down to the train validation steps over here, I split the dataset into 3 sets. 40,000 images for training, 10,000 for validation, and the original 10,000 test images were kept separate. The validation set lets us monitor overfitting during the training without touching the test set. And here are some of the examples of the images. You could see, like, you could kind of make them out, like frog, truck, another truck, deer, there's a automobile, bird, horse, ship here, and a cat. So first of all, we deliberately over parameterized the CNN. We did this because it has 2 convolutional blocks with 64 and 128 filters each, followed by a dense layer of 512 and 256 neurons. This gives it over 1 million parameters, which is way more than needed in this task, but more importantly, there's no regularization at all. And I trained it using only around 15 epochs. And if we scroll down to the graph itself, we could clearly see like a overfitting problem. If you look at the accuracy plot, and the training accuracy keeps climbing, but the validation accuracy plateaus or even drops. The gap between the 2 lines is the overfitting gap, and the loss plot tells us the same story. Training loss keeps going down while validation loss starts increasing. And this model is essentially just memorizing the training data instead of learning the general patterns and the features. To address the overfitting, first we used the technique that combines L2 regularization and dropout. So L2 regularization adds a penalty to the loss function based on the size of the weight, and this discourages the model from relying too heavily on any single feature. And I set the weight decay to 0.001, and then dropout randomly sets a percentage of the neurons to 0 during each training step. I used 25% dropout after the convolutional blocks, and then 50% after the final output layer. This forces the network to learn redundant and more robust representation. And then if we scroll down to the graphs after, comparing these curves to the baseline, you can see the gap between training and validation is now much smaller, and the model isn't memorizing as much, it's generalizing better, and the validation accuracy is a lot higher too than the baseline, as you could see. Our second technique was data augmentation. So instead of training the images, the same images every epoch, I randomly applied transformations, rotations of like 15 degrees, horizontal flips, like small shifts, slight zooms, and you can see like 10 different variations over here. So each epoch, the model sees a slightly different version of every image, which prevents it from memorizing each specific like pixel patterns for the image. And then if we scroll down once it's done trained, you could see when I try to combine data augmentation with L2 and dropout, the training and validation tracks even more closely. The training accuracy is a bit lower than before because the augmented images are harder, but the validation accuracy holds up pretty well, and that's exactly what we want. So we want our model to learn and to generalize. If we scroll down, we could look at the over parameterization analysis. So here's a summary comparing all the four models. You can see an overlap fitting with the baseline has the largest gap, and it shrinks as we add regularization. And the augmented model with L2 and dropout has a smallest gap, which often is the best for test accuracy. Here's like a summary table comparing all the models. You could see the overfitting gap column, and the baseline has the largest gap, and it shrinks as we add regularization and L2 dropout, and the smallest gap is with the augmented model with L2 and dropout, and it often has the best training accuracy as well. And then if we scroll down, here's a bar chart I made. It's a visual to see how close the training, validation, and test bars are for the regularized models compared to the baseline. And then finally, we have like a validation versus loss versus epoch chart. This shows all four models across the epochs, and you can see the baseline validation loss starts to increase after a few epochs. That's why where overfitting kicks in, and the regularization models are much more stable. This tells us also the optimal number of epochs for each model for the baseline, and we'd want to stop early around like 5 or 6 epochs, while the augmented model can definitely benefit from more training. And to summarize, I demonstrated overfitting using overparameterization in CNN on the CIFAR 10 dataset, and then showed 4 ways to reduce it using L2 regularization, which penalizes the large weights, dropout that forces redundant learning, data augmentation, which provides more varied training examples, and reducing the model's size, limits, and memorization capacity. And then combining these techniques gives us the best generalization performance. Thank you for watching.